Okay, I've got some worked examples here for integration by substitution for the reverse chain rule. We use substitution quite a lot in integration, but not always for the reverse chain rule. However, these examples are to do with the reverse chain rule, and let's just remind ourselves what we mean. So if we observe that the derivative of a composite function here is going to give us this, which is the derivative of the g, the outer function, with respect to f of x, the inner function, times the derivative of f of x. Then if we just turn this around, if you like, integrate both sides, perhaps, then if we've got something of this form, then that will integrate back to that original composite function. So the trick really is to recognize that our integral is of this form, and then we can, that will give us the way to the solution. So here's the first example, and it gives us the substitution to use. Yeah, 2x over 4 plus 3x squared to the power of 2. It kind of helps in a way to think of this as all on one line. If you see it as 2x times 4 plus 3x squared to the power of minus 2, somehow that actually it sort of looks more like a the reverse chain rule possibility. So what we're doing here, well, let's do this substitution as they say, and that's going to give us du equals 6x dx. That's just differentiating that, and therefore the integral becomes the integral now of actually denoted x equals 0 here. So that just is reminding us that these limits on this definite integral are x limits, so we don't get confused. So we've got 2x as r from there. Then this is becomes u squared here. And then because du equals 6x dx, then dx is being replaced by du over 6x. And if we simplify that, we can actually our x's will cancel. The 2 and the 6 give us a third, which I've taken outside the integral, and therefore we've got the integral, again, x limits 0 to 2 of 1 over u squared. That's going to integrate to minus 1 over 3u between those x limits. Again, if we substitute this back in for u, we can drop the x equals. We just know that those are x limits now. And then if we just evaluate those between those limits, then we're going to get this result. So that's how that works. Let's just have a look at another example. Okay, so find this integral x squared plus 2x over 2x cubed 6x squared plus 1. Well, again, if I write it like this, it does become a little bit more evident that this is actually the derivative of the inside function, the f of x. So let's have a look. So if we do the substitution, we have to work this out for ourselves, but obviously, now we've written out like that, it's sort of fairly obvious to see what the substitution is. 2x cubed plus 6x squared plus 1, giving us du equals 6x squared plus 12x dx, and dx equals du over, taking 6 outside, the factorizing out, x squared plus 2x. Okay, so if we rewrite our integral, then we've got our 2x squared plus 2x from there. That's there. We've got, this is u, it's u to the power of minus 1, so that's that. And then we substitute our dx for this du 6 into x squared plus 2x. Well, These two cancel out, and this is always the pattern you get with these reverse chain rule substitutions, giving us, well, basically this 1/6 du, and then we can integrate that to 1/6 natural log of u, and then we can put our x function back in for u, and it's going to give us this this result. Okay, so that is that one, and the final example, well, pretty much on the same lines, really. If we write the integral like this, so this is the integral between 1 and 2 of 1/x cubed times e to the power of 4x to the power of minus 2, and a pretty ugly looking thing it is, but again, if we bring this denominator up and write it as a negative power, we actually see that the inner function, I mean, this is a composite function, isn't it? The outer function is the exp, and the inner function is 4x to the power of minus 2. So the derivative of the inner function, the f, if you like, is going to be, you know, some constant times x to the power of minus 3. So that's essentially, to within a constant, we have got f prime of x here, the derivative of f in there. So if we do the substitution of u equals x to the power of minus 2, giving us du equals minus 2x to the power of minus 3 dx. And what I've done here is I've, just because I know I've got this x to the power of minus 3 dx here, I've isolated that, equated it to du over minus 2. So when I come to do my substitution, again, I've used the x limits here, I've got them explicitly as x limits. We've got e to the power of 4u, because this is u here, it's the power of 4u, times, well, this expression, as we've seen from over on the right here, is du divided by minus 2. Okay, so it's minus a half, isn't it? And then if we so if we integrate e to the power of 4u du, we're going to get a quarter e to the power of 4u. Substitute back in for u, which is rx to the power of minus 2 there, and we basically get this evaluated between 2 and 1. Right, we can do that. I mean, x to the power of 2 to the power of 2 is 4, to the power of minus 2 is a quarter, to multiply by that 4, that's going to give us 1. And then if we evaluate it at 1, we're going to get 1 to the power of minus 2, which is 1, and so all this will be e to the power of 4. So just a little bit of manipulation, I'll say no more than that. We're going to end up with this thing, which, if we want to write it in its kind of simplest form, is going to be this e to the power of 4 minus e to the power of 1, all divided by 8. Okay, so yeah, the key thing, as I say, is to recognize when we've got something of the reverse chain rule form, and then that's going to advise what substitution we will use. Okay, I mean, there's all sorts of similar problems with trig functions and so on, but I think that helps to illustrate the principle of the reverse chain rule quite well. So hopefully that's been helpful, and I'll see you next time.